Okay, well, welcome everyone. What you see here on the screen is actually the San Francisco Bay Area. I guess most of you guys have been there, and our office is around here. Sorry, it's around here. And what you see here is some moving ships in the Bay Area using AIS data that you can download for free. And actually, this picture on Google Earth is drawn straight from AllegroGraph. So all the coordinates are in a triple store, and we can do all kinds of interesting calculations on this data. And today I'm going to talk about kinds of things you can do with geospatial and with moving objects. So let me go to my presentation. So I'm going to talk about geospatial processing and tracking moving objects in an RDF graph database. So a little bit about what I'm going to talk about today. I'll try to keep it in about half an hour. So I'll say a few words about RDF graph databases. Then I'll talk about why geospatial is important, and I'll show you some real-world applications where people use geospatial indexing in a triple store. So I'll talk about something we did with Google News. I talk about a production system at Siemens, and I talk about something we do for an online bank. And when I do this online bank demo, I'm also going to show off how we can do geospatial, temporal, and social network computations straight in SPARQL. So very exciting, the new capability in 4.12. Then I'll move into moving objects in our 3D indexing. I'll talk about some applications, things that people can do with 3D indexing, and I'll talk about a little prototype that we created for a command and control system in the military, and it will also give me the opportunity to show off our call-off-based rule system. I might say a little bit more about the ships in the Bay Area if I have time enough, and then we're also doing research in doing more and more complex 3D calculations, and I'll give you a little bit of an overview of the complexity of this, and we actually have a paper about this that you can read later, so I won't go too deep, but you might find it interesting to see what we do there. All right, so about graph databases, I guess most of the audience is deeply familiar with that. So this I usually explain it. I say a relational database has rows and columns. We actually have nodes and links between nodes. This is typical for graph databases. RDF graph databases actually are much more powerful because in an RDF graph database, the nodes and the links are unique URIs. So people in multiple locations can make their own databases. And as long as they make sure that they use the same unique names, you can very easily link all these databases together. And on top of that, it's all based on W3C recommendations. And in RDF databases, it's also really easy to do hypergraphs. And in about a week, I'm going to talk about scalable hypergraphs in a triple store. All right, so that's all about RDF graph databases, but I promised to talk about geospatial and moving objects. So we've been talking at France about geospatial reasoning, I think, for the last 5 years. Yeah? So about 5 years ago, we started to add geospatial features to our triple store. And one of the things that we're really good at is at proximity search. So if you have, say, a bunch of events that you store in the database, where events are defined as things that have start time, end time, some actors, and then a location, then we make it very easy to find all the other events of things close to a particular point. But in addition to that, we also offer, say, polygons and computation on top of polygons. All right, so that's all about the geospatial indexing. And then we have a bunch of examples that I usually like to show when I talk about geospatial. So the first example is one where I spidered Google News and Bing News using this kind of framework where we can take spiders, feed them by URLs and word lists, go to the web, get the text out of web pages or other pages, then apply entity extractors, so we get names out of a text, place names, people names, organization names, currencies, maybe even important events. We store all that in AllegroGraph and in Solr, and then we take the objects to be found in the text and link that all to, say, Freebase for organizations, GeoNames for places, DBase for DBpedia for people names, and then we make it all available in our graph visualizer and navigator. Yeah. So, as I said, we have this demo where we extract people, places, and organizations. We link all these people to the linked open data sources, and then this is something we can do. We can do very complex queries like, which Republican talked to an oil company less than 100 miles from Tampa 2 weeks ago? Yeah. Or which scientists are mentioned in the news yesterday that also mentioned the city that was less than 100 miles from Tampa? Things that you never would be able to do in Google, although Google is working really, really hard on the knowledge graph, so I expect that in a few years you can do the same queries in Google. All right, so this is the demo. Let me go there. So I have 1 day of news for Google and Bing, and I can look at something like Obama and health care, and I can look at these articles. Yeah, and then you see a particular text, and this text 177 has a bunch of concepts that came straight from the entity extractor. In this case, it was Cogito. Here were the particular topics of this text. Yeah. So here's the triples, by the way. Text 177 has domain, company, subject, predicate, object. Yeah. There's some important concepts. There were a number of organizations. There were a number of people in here. So here's the people that the entity extractor found. Here's some places that the entity extractor found. And then what we did is we went, for example, for the places into the GeoNames, and we linked it up with the GeoNames. So here you see some triples for a place we found in a newspaper article and added that to the database. So now we found that this place Alpha in New Jersey has this particular latitude longitude, it's a populated area, etc., etc. So you understand how we can enrich this data, and then I can explore this graph on the screen and look at, for example, at the organizations, people, and places, and I could explore this text and see what these things have in common. So I could choose a few parts, and I could take this, I could take this one, I can see how they all link up. Yeah, and before you know it, you have a graph so that you can investigate how these articles actually all link together. Yeah, so this is how you explore something that you got out of the news. You can focus in, and I could continue to see whether we knew anything more about other places. But let's go to the query. So what I wanted to show you is how we can do geospatial queries over text about entities that we extracted out of text that we kind of spied from the web. And so I can go to the query view. And first let me show you a query where in SPARQL you try to find all the scientists in the news in a particular day. You would say, give me every text where there is a name X, where this person X is the WordNet type scientist. Yeah, and I would find that there's 5 scientists that were in the news that day. I could create a visual graph. Yeah, I would say this is the scientist. Here are the 5 scientists, and I could actually see, so how are these texts actually related? There's a lot of ways these things are related. Yeah, and so I would find how Arthur and Henry were related to, well, House of Representatives, this particular people here, commerce, etc., etc. But that's not the point today. I wanted to go to the geospatial. So you notice this is a SPARQL query, but you kind of can imagine that it's really hard to type this in and to remember the types. So we actually added on top of that a user-friendly prologue layer, and I can do queries like this. Let me see here. Find WordNet scientist geo user-friendly. Yeah. So I'll give you 1 second to read this. Yeah. Basically what you're asking for, give me a text with city in radius, where I have a text, I have the city Tampa, 100 miles, and give me all the places that are within 100 miles of Tampa. Yeah. Where there's also a text, yeah, this text has a person that is a scientist, and this text has a particular title, and then I can do the query, and here I find that text 540 has a person in the place, and then a particular title. Yeah. So this is a simple example of how you can add geospatial capabilities to your data, and you can enrich the queries that you can do. Yeah, simple example. Any questions so far? Okay. Let me exit this tool. Yeah, so it's the first demo. Now, do people actually use this in the enterprise? Well, recently Siemens Energy went into a production with a system that helps salespeople within Siemens know everything about the turbines that they are maintaining and selling all over the world. And Siemens is one of the biggest players in the field of energy turbines. Yeah? And their problem for the salespeople was that if they wanted to know about a particular area, about particular components of a particular turbine, then they had to look in far too many databases. So what a team within Siemens did is they built kind of a mini Watson and to natural language queries for salespeople. Yeah, so a mini Watson. And so the kind of things that the Siemens salespeople could ask is, what is a megacluster, give me the active units in China, what's the service region of New York, and going on with queries that, for us normal people, have no meaning, but for them, these are important questions. And what they actually did is they took information from all these databases and about places and things, and they linked part of the information up with Wikipedia, part of the queries with Freebase and GeoNames, so that they actually could answer geospatial questions. And of course, all that metadata was stored in AllegroGraph. And this system was a finalist for the Siemens Innovation Prize in 2013, the candidate for the AAAI 2013 Best Paper Award, and the system saves more than 10 million euros per year. So this is kind of a cool system that is doing live geospatial capabilities. Okay, so then another system that we're working on that needs geospatial capabilities, it's a system that we do for a bank where we look into fraud. So what we're trying to find is fraudulent patterns in accounts and transactions between accounts. To give you a simple example, would be what they call collusion. One or more people work together to rip someone up and then let the money flow out of the bank into foreign credit card accounts or foreign banks. So what might happen is a pattern that you might look for is, say, give me more than 5 accounts opened in 1 hour, yeah, and then within 30 minutes, other accounts pay large money into these new accounts, and then in the next hour, money flows into external accounts and credit cards. Now, this still might be harmless, yeah. I mean, this might happen all over the place, but it might become a suspect thing if you can kind of find out that the people that opened the accounts had somehow close connections, like they opened an account from the same IP address, or they did business with each other in the past, or they did it from the same place. So suddenly we have some geospatial questions here, and we do the same thing for the people that paid money into these newly opened accounts. So what you see here suddenly is that you need graph search, and you need temporal search, and you need geospatial search all at the same time to find very complex patterns. All right, so, and I actually can demo the system, parts of it. So here's the basic data. You have some accounts over some time with an IP address, with email, and a particular location. And there's events, like payments between accounts from some IP address at some location at some time, and then of course senders and receivers and the amount. So let me demo that. So I'm going to my desktop, and I open I just first want to show you the data. So let me open raw data. And then let me show you some data. So I'm looking for a person called Bruce, something. And I find one person. And let me double click. And here you see some triples for Bruce. Yeah, you see this person opened an account on this universal time at this IP address. This was the new account number for this person. He opened it in a city called Gun Barrel City. So if I click on that, I go straight into the GeoNames database again, where you see information about Gun Barrel City. This is in Texas, very small town with only about 6,000 people. And here's the latitude longitudes. So going back, I'll go back here. And then you see that this person paid some people. And well, let me not go too deep, but let me go to an event. So this person was the receiver of this particular transaction. So we're jumping into a transaction. So here you see some triples for transactions, which was made at a particular time, not in Gun Barrel City, but somewhere else. Yeah? And the receiver was Bruce, and the sender was Dave, etc., etc. Yeah? So accounts data and event data linked together. Yeah? So if I go to graph again then, and I want to explore the graph just by looking at, say, sender and receiver relationships, I could click on this one. I could click on this. Reformat it a little bit. I can click on here, and before you know it, yeah, you see that this is a network, a graph made up by. Okay, this doesn't connect. Let me see if I can find a connection between the two. Yeah, before you know, you get a beautiful graph of how everything is almost connected to everyone else through small, medium, large, medium payments. Yeah, so this is the data and how it looks like. So how do we do now geospatial, temporal, and social network questions on a data set like this? Well, you can go into the server and starting the server. I have the database already open. I can do some queries. And first let me do a little social network query. Okay. So this is a query where I say, okay, find a person with this email address. Then, and this is what they call a magic function. Yeah, so this is not a predicate in the system, but this is a computer function that we can embed in SPARQL, where I say, compute a group around the person who, that I found here, go 3 levels deep and use the paid relationship. But this paid relationship could be a single predicate, but it could also be a complex SPARQL query itself. Yeah? And then what we do is we compute for every element in this group the centrality or the importance of that particular person in the group. Yeah? So this is another magic predicate. So this was a real SPARQL query, yeah, where email is actually a predicate. I found a group, I computed the importance of a person in the group, and then I say for every member, well, I need to get all the members, you get the email address, and then you do this computation. So this is embedding social network analytics in SPARQL. I can do geospatial, payments within 10 miles of Woodbridge. Yeah. So I say, well, I have a town called Woodmere. Actually, it's wrong. It's not Woodbridge. It's Woodmere. Place New York. Yeah. That happened in a particular place. That has a location, and then give me all the other places that are within 10 miles of this location. Yeah. And then the rest of the query, and I can find how many payments were made there. So this is a way to embed geospatial in SPARQL. And then, of course, I can mix it all together. So I could do something like this query where I say that the most important friends of Sonia make a payment within 100 miles of Rotterdam in the last 10 years. And I'm not going to read the SPARQL query to you, but it executes pretty fast. And in this case, it's chock full magic predicates to make this query work. Yeah, so this is an example of our new SPARQL available since 4.12, where you can mix temporal, geospatial, and social. And if you want to build your own smart predicates or complex functionalities, you can just use this and embed it in your own SPARQL. All right, so let's continue. So this was a demo of this bank. Let me close this. And go back to my presentation. Yes, so far it was about objects and about geospatial, but not about moving objects. So we have been looking to moving objects. And the newest thing we've done is we created a way to do 3D indexing. So far it was all 2D indexing, but since recently we have 3D geospatial indexing. So for 2D indexing, we actually divided the world into strips. Yeah, so you could say, well, I divide the world in strips of 5 miles, and then we would encode that into our internal numbers for parts of triples. So if you look at our triples in AllegroGraph, each part of a triple is actually represented by 12 bytes. And then within the 12 bytes, we can store away a particular strip for a place, and then the longitude and the latitude, and do some all kinds of interesting indexing that's described on our website, so that you, in general, you use only one disk I/O to get to a particular thing that you were looking for. This is for the purely tech guys, so let's not go too deep here. Yeah. So, so as long as you choose your strip size wisely, you can reduce the number of I/Os and get your data as fast as you want it. So we did this first for 2D, and now we have a 3D version where we no longer have strips, but where we can take a space and divide it in blocks and then use roughly the same kind of indexing. So again, use minimal I/Os to get to the point where we think that our data is. Now there's all kinds of applications for this. We're doing biodiversity projects. The objects move around. We have an agency that tracks ships near the coast of Africa with satellites and wants to figure out if one of those ships has malicious intentions or not. We applied it to fleets of trucks and swarms of airplanes. One company is doing a POC where they track data for soldiers, because in modern days every soldier is walking around with location tracking technology. And then, of course, there's telco services that use this stuff. And one area where we used it in is in a POC on command and control using 2D and 3D indexing. And I'm not going to say too much about this because I'm already close. So I'll probably give a whole webcast about this one. Yeah, but just, let me see, where am I? Oh, here. Yeah. So the goal of this particular POC was to build a command and control system that integrates intelligence and sensor readings from divisions, brigades, battalions, and companies. So in general, when you have all these different parts of an army, they each have their own sensors and information sources. And so it's very, very hard to integrate all these at the same time. So they're building a new command and control system that actually can take all the information sources from all the different parts of the hierarchy in the army and integrate it in one area. So what they have is, what we built is a POC where a battalion tried to capture some enemies in these particular areas. So there were 2 battalions going forward. By the way, I'm not going to tell you where this is, but this is actually Canada. So this is just an example map that we had. And so, so here's how I'm going here. Yeah, so there were some anti-tank posts, or potential anti-tank posts that we know about. There are some caves where people might walk around, where we know that people can hide stuff, or can hide weapons. So you see these caves here. And then at some point, the battalion starts going, and they already know that there's a few anti-tank posts there. Yeah? Then you keep going, you cross the border, and then somehow someone hears that there's 3 people from the Donner village that are planning to meet at a particular cave. And then you keep going, and you find that some civilians are moving west toward open terrain. And then even later you see that they're actually walking close to the cave E, and that they actually might enter in that cave, so they go into the cave. Then also at some point you might see that there is some cars that move to another cave with civilians in it again. And then they, going out of this cave, they go to open terrain again, etc., etc. So I'm not going too deep into this example because this is something I can do later. But the interesting thing is that we built several hundred rules to modify hypotheses about where certain dangers could be. Yeah, so you have all these caves, potential anti-tank posts, other things that could be very, very dangerous, and you might have a hypothesis about each of them. And at any point in time, you want to get the danger level for everything that you think that might be important. So this is a rule that says if there's a place that can be used to store ordnance and people enter and leave this place within an hour, and we are closer than 2 miles from this point, then it's 5 points to the danger level for the hypothesis that this place is dangerous. Okay? So this is encoded in some kind of prologue. And if you're interested, then read it later when you get this presentation. But this would temporarily make a particular anti-tank post more dangerous. Yeah? So this was an example of what we did with this moving objects data. And then let me go here. So another area where we did this was for AIS data. So if you ever want to play with moving objects yourself and you find it hard to get data, just go to the website for marinetraffic.com. They have an API, and they will give you the data for all the ships that you have, and then you can just play around with all the geospatial calculations that you want to do. We actually used it to look at traffic in the Bay Area. That was the picture that I opened with, where we computed whether ships were there, well, how often they came there, whether they always went to the same place, or whether they usually went to the same place and sometimes went to a different place. So you want to find patterns that looked at out of the ordinary, and we created a bunch of algorithms to find that. Okay, so that's about examples about moving objects, and then finally I conclude with some research we did about the complexity of geocalculations. So, and we actually have a paper about this by Steve Huffley, and we'll make that paper available after this meeting. It's probably already on the website and available. And so for our 3D indexing, we divide the world into blocks. And so if you just have a simple question like, what is within a given bound from a given let long time, yeah, for a particular place and time or location in time, then we just have to look at a few blocks. But if we want to know whether 2 moving objects were within a given distance from each other, then it's already harder, because now you have to compare multiple stripes within your blocks world, and then increasingly say you have a moving object, find all the moving objects that were ever within a given distance, and then find all occurrences of 2 moving objects within a certain distance. And then the hardest that we describe in our paper, which is actually almost intractable to do, is to detect potential moving object clicks. So objects, they're always close together. Yeah? And so we do the calculations. This is by far the hardest we ever can do. And so just take and find this paper on our website, enjoy it, and with that, I want to conclude our presentation. So thank you very much, and let's see what kind of questions we have. Okay, is the Siemens paper available? Correct? Yeah. Okay, yeah. If you go to our website, you go to the white paper section, then you go to AllegroGraph white papers, and you'll find that paper there for Siemens. Another question. So, is this geotemporal and social capabilities, are they available now? Yeah, I think I already answered that. I mean, If you get 4.12, then all these capabilities are available. If you want to find them, go to our website and look for magic properties, and you'll find information about these capabilities. Oh, here's a question, interesting. Are SPARQL 1.1 features like group by and property paths supported in Prolog? No, not directly. If you want to do that, you have to program them in Prolog itself. But as you know, Prolog is a full Turing equivalent language, so you can program these things yourself. But no, only SPARQL has these directly. When is the okay, last question. When is the 3D Geo going to be available? Well, yeah, we already have it available internally, and we expect it to have available in 4.13. Yeah, so the current version is 4.12. We expect this to have in 4.13. Oh, this is an interesting one. Will Graph be able to connect to SPARQL endpoints? Yeah, actually, we recently started working on this, so that Graph would also work with other triple stores and with SPARQL endpoints, and we already can play with DBpedia right now and use Graph to go directly to the DBpedia. One problem is that we do a lot of shortest path calculations in triple stores, and most triple stores don't provide a direct API to create generators or to do shortest path from an API. So we probably have to ask other vendors to provide it as an API so we can make Graph work with them. Okay, that's it. We've got some other ones here that I'll try to make bigger. So I'm going to work through a couple of those there and then we'll wrap it up. How does Solr for indexing work with an RDF graph database? Yeah, I just quickly mentioned that, but the person that asked the question probably knows that Solr works with XML objects or JSON objects. So as long as you make sure that one of your objects in Solr has a unique ID, then we'll have one triple that has the same unique ID as the object. We use it as a joint variable. Now we actually can do Solr queries directly from SPARQL. So I hope that helps. And we actually have a webcast on our website that shows how we work with Solr. So it's probably 1 or 2 years ago, but if you go to our previous talks, you'll find that. Let's see another query. Could Hadoop bring anything to the architecture you have shown? I mean, mostly MapReduce or Yarn. Well, we actually are working together with Intel, who is building a new product called Graph Builder. So that they make it very easy to extract graphs out of Hadoop. And if you go to our website, then you see under the category News and Events a talk that I gave that is called Augmenting Hadoop for Graph Analytics. Oh, sorry, no, I'm going to give that talk. Sorry, I gave that talk at Semtech. I'm going to give the talk at November 20th at 10 o'clock at the same time. Last one, does AllegroGraph systematically rely on ontologies? Well, AllegroGraph completely supports ontologies. We do both RDFS++ reasoning, and now we also do a full OWL to RL materialization. But a triple store is basically can work entirely without ontologies. Yeah? If you don't want to work with ontologies, you can just use the flexibility of an RDF graph database to add whatever data you want, add new predicates, classes, whatever on the fly. But if you want to, you can add ontologies and constrain your database that way in all kinds of meaningful ways. Okay, thank you very much.